All right, so we are now moving into multivariate 4. As you can see, we are now moving into the interpretation of those OLS coefficients. We'll spend some time on that today. So let's say we've got some multivariate regression outputs. As you know, first thing we did, we looked at the significance of the entire model. That's the R-squared term. That's our goodness of fit measure. Next thing we want to do, we want to look at the sign, right? So what is the sign of what is the relationship between x and y? We look at the sign for the coefficient. Fairly straightforward. Looking at whether or not it's significant, you look for the p-value, 0.05 or less. So now that we've done that, what do we do next? Well, the beta coefficients, as you recall, are the slope that we used to draw a regression line that illustrates the relationship between x and y while considering other factors. That's a multivariate regression model. So it tells us what the impact of a variable is on our dependent variable while considering everything else. In this case, as you recall, we looked at the same regression last time, and we looked at income. It was not statistically significant. In this case, incumbency, or INC, is significant, so we're going to practice interpreting that. In this case, the beta coefficient is 0.083. So for every unit increase in incumbency, we expect a 0.083 increase in Democratic vote shares for presidential candidates in 1996. That's what our variable, or our dependent, okay, DP96. All right, so the general boilerplate language here is that for every unit increase in x, we expect a fill in the blank, there's where you put the beta coefficient, increase if it's positive, decrease if it's negative in y. So again, boilerplate language for interpreting a beta coefficient is as follows. For every unit increase in x, we expect a, wherever we put that beta coefficient right there, increase or decrease in y. So you add the beta coefficient in that blank space. It is now no longer blank. But let's say you really want to impress someone with your interpretation of a beta coefficient in a regression model. What is the A+ response here? Here, you could plug in values into the OLS equation. As you recall, the OLS equation is that simple linear equation we covered in middle school and high school, y equals A plus bx. In this case, however, since we have more, our line will look something like this. Y equals A, which is your constant, or alpha, plus bx1 and bx2 to represent the fact two variables in this particular model. What do I do to get the x values for my equation? Well, the answer lies in your descriptive analysis. Here, mean, minimum, and max values will come in handy. So what you really want to do is you want to be able to plug in values. The constant, you know what it is. The beta coefficients, you know what they are. They're not going to change. The one thing that will change are the x values that you give for each of those independent variables. Now, in this case, typically you wouldn't have to really plug in the x values for a variable that's not statistically significant. That's okay. We're going to do that here just so you get a little bit of a taste of how you would create this line. And what we're going to do is we're going to keep that one variable that's not statistically important to us, let's say income, we're going to hold it constant. How do we do that? By holding it right here for x1, we're going to use a mean value, and we're not going to change that, okay? However, for x2, which is incumbency, we're going to allow those values to change just a little bit. Let's say in this case, we'll do the minimum and maximum values. So again, for incumbency, we're going to use this mean value right here, and we're going to leave that alone. And for for income, we're going to leave it alone, and for incumbency, we're going to use these two values down here. So let's say we try this with the minimum value and a maximum value. As you can see, we're leaving this the same, this is the same, that's the same. Those are our beta coefficients and our constant term. And we're going to leave this value here for income alone. We're not going to let it vary. But we are doing some really interesting things here with the x2 variable, allowing it to change one equation to the next. So what that will give us is it'll tell us that the Democratic presidential vote share for this circumstance where there is no incumbent is, let's say, 22%. But when there is an incumbent, it's 23%, right? So we're going to get to see that change, that increase over time. So what this does is it really tells us how y changes when incumbency goes from -1, non-incumbent, to 1, where we have an incumbent. This is known as a margin in data, and it really helps you draw your line in your data and helps you discuss your results in slightly less robotic tone. So this is what I mean about when I said last time that you can interpret these coefficients like Spock, or you can interpret these coefficients and interpret your regression equation like a really savvy political scientist who knows how to speak to other humans. So this is the way in which you would do that. We'll talk a little bit more about this and get some practice doing this with our data as well. All right, so to recap, what do you know so far? You know what OLS regression does. You know that it's intended to provide you a multivariate analysis of the relationships between various x's, and particularly your independent variable of interest and your dependent variable, right? It does so by drawing a line. It does so by using a sums of squares algorithm, which, among other things, translates all the independent variables into the same language of the dependent variable. It's the reason why we can use that boilerplate language for every variable. Every time it's translated, those beta coefficients are translated into units of the dependent variable, which is what makes OLS regression relatively easy to interpret. We've also focused on how to interpret a goodness of fit measure for OLS regression. That R-squared term speaks directly to your research question, so you now have an answer to the question that you posed in 215. Third, we now know how to interpret beta coefficients to help provide some sort of answer to your hypothesis. Either you show some support or you don't show some support for your hypothesis. And we can do this because we can interpret that beta coefficient by looking at the sign, looking at its significance, and then interpreting the coefficient to see what the impact is on the dependent variable. All right. And you now have a couple different ways in which to do that, boilerplate language and some margins that you can construct. So what's next? Well, what's next? We're going to consider a couple things that could go wrong in OLS regression and some things that we can fix, and then we'll start talking about logistic regression, which is a very close cousin to this model. It does, however, calculate things a little differently. Instead of translating everything into units of the dependent variable, it speaks in terms of likelihoods or probabilities of something occurring. The other thing that's important to keep in mind with logistic regression is that it only is intended when your dependent variable is binary or dichotomous, right? 0, 1. Otherwise, logit is not going to fit the bill. All right, see you next.